Yes, whoever is Rana Dagubati, you have a doubt? Are you one of this class or are you of a different class? And guys, please use your real names and numbers, because if your name is anything other than what your actual name is, you'll be removed from the group. So make sure you're using your real names, because attendance matters over here. Since everything is recorded, each of your name will be seen in the recording, and your attendance will be taken in that manner. So please make sure you use your actual names. 17 participants, not many. Okay, can I start? Can I start? Give me a quick answer. Can I start the session? Okay, great. Right. So in the previous lecture, we have seen different examples. I mean, different scenarios where you get to design a masonry wall. Uh, this is the previous example. In the first example, you got to design the masonry wall which has no lateral supports. It's purely the internal wall without any supports that is having and superimposed loads on top of it. In the next example, please mute your microphones, Sriharsha. Yeah, thank you. In the next example, you got to design the internal wall which has lateral supports to it. Lateral supports to it. So when you're having lateral supports involved, you will have to refer a different set of tables. Table 6, I think table 6 for lateral supports. And you will have to use a stiffening coefficient in order to take the lateral support into picture, because when you add a support in terms of a cross wall or a pier or a buttress, this will give a more stiffening effect to the entire wall, which is ought to be designed. So in today's example, we are going to look in a much more real-time scenario where you get to design the masonry structure, I mean the masonry wall, which is holding an RCC slab on top of it. So this is the masonry structure which I just modeled over here. So you have your external walls in the end, which is depicted in gray, and you have your internal wall which is depicted in brick masonry, which is the one which we have to design. So let's just get on with the question. A solid wall with piers. So when we are talking about piers, if you see this little projection which is happening from the interior wall, these are called as piers, and previously these are cross walls. Okay, so cross walls are nothing but those are full scale walls which are connecting or interconnecting the main masonry wall. But for piers are just a little extra projection that is happening to a main wall, so that it will give more amount of stiffening or more amount of support in terms of rigidity to the entire wall structure. So we have a solid wall with piers over here which we have to design. As the question says, design an interior wall of a single storied workshop of height 5.4 meters. So the height of this particular workshop is 5.4 meters. That is the clear height. Let me just depict that over here. So from here to here, this will be 5.4 meter. Okay. The height is clear height is 5.4 meter, supporting an RCC roof. This is your RCC roof. The bottom of the wall rests over a foundation block. Assume the roof is equal to 45 kilonewton per meter, that is the roof load. This is the figure, cross-sectional figure, that is given for reference. So of course, below this particular masonry wall, you can expect a foundation. I didn't model that over here, so just exempt that out of the model. So the thing is, let's walk through the entire design procedure first. The first thing is that you need to calculate all the weights that are happening on the wall, be it the live load, be it the dead load, be it the self weight of the brick masonry itself. The live load, as in if there is any live load that is happening on top of the wall. I mean, since this is a masonry RCC slab, you might have some people that are standing on top of the slab, so you will consider the live load of it. You will consider the dead load of the RCC slab itself, that is the self weight of the slab, and any other load that is being imposed, be it self weight by the virtue of any other eccentric load that is happening. Everything included, it is given in the question that the roof load is equal to 45 kilonewton per meter. That is the total live load and the dead load, that is the self weight of the roof acting on the masonry wall, that is the center wall which we have to design, is 45 kilonewton per meter. Now choose the wall thickness. The wall thickness is equivalent to 200 mm. Let me just depict that in the diagram as well. I'll just remove the slab on top so that you will be able to see a cross-sectional view out of it. Yeah. So if you see the view, the plan view of this particular structure, yeah, the center to center of a bay. Now a bay is nothing but, see, in this particular structure we have 4 bays. I have just modeled 4 bays. They can be many, but for this particular structure there are 5 piers and 4 bays. Now each bay is enclosed between 2 piers, and the center to center distance from the pier to the next pier is the span of bay which we consider, which is 3.6 meters over here. So the exact center of the pier on the either side is the distance between the exact centers of the piers will be 3.6 meters as given in the question. Next, the width of the pier is 200 mm, like it's given in the question. The thickness of the wall is equivalent to 200 mm. Thickness of the wall, as in the thickness of this masonry wall, this one. I can show it in measurement over here. The thickness of this masonry wall is from here to here, it is 0.2 meter, that is 200 mm, which is seen over here. Next, the thickness of the column on either side of the wall is 100 mm each. Okay, column is an ambiguous term over here. Let's just keep it to pier itself. Let's not say column. The thickness of the pier on either side of the wall. So this is your wall which is in the center, and this is the thickness of the pier that is happening on the other side and on this side of the wall. So there are 2 sides of the wall, inner and outer. So on the inner side it is 100 mm, and on the outer side it's 100 mm as well. So the thickness of the pier, here it's written as column, on either side of the wall is 100 mm each, which is depicted over here as 0.1 meter. Moving on, assuming that the crushing strength of the brick units is 10 Newton per mm square and M1 type mortar is given, the basic compressive strength is 0.96 Newton per mm square. This is given with regard to table 1 from your IS 1905. I can just show you for reference because you might have forgotten. Just let's recall that. In IS 1905 table 1, this gives us the grade of mortar and the minimum compressive strength that particular grade will offer you by the end of 28th day. So let's just pull this down. Okay, so as per table 5, in table 5 this gives us the basic compressive strength values. So in table 5, which is table 8, my mistake, in table 8 the basic compressive strength values with respect to those particular specifications, that is 10 Newton per mm square and M1 grade motor, and 10 Newton per mm square, which is over here, 10 Newton per mm square and M1 motor, it is giving 0.96 Newton per mm square. That will be the basic compressive stress that can be offered by that particular combination of choice. Now, let's get on with the total load calculations. Now, over here, when it comes to the load calculation, it happens with respect to bay. Now, if we are able to calculate the total load with respect to bay, it is easy to calculate with respect to any number of bays, because it's more like a unit measurement. So the length of each bay from center to center of the pier is given as 3.6 meters, and the total roof load acting is given as 45 kilonewton per meter. Is given as 45 kilonewton per meter. Guys, please mute your microphones. Yeah, 45 kilonewton per meter. Now the total load for 3.6 meters is, it's a simple math, 45 is per meter, 3.6 meters is what is required. So that's 162 kilonewtons. That is a total of 162 kilonewtons is acting on the wall. Now when I say wall over here, we are just trying to see this particular element. Let me just pull this up so that it will be much more clear. I'll just push it out. Okay. So as you can see, that particular load, that 162 kilonewtons of load is only acting on this section. This is one bay, and this is this is what the load is acting upon. Now, next is that we have to calculate the self weight of that particular wall. So the self weight of the wall is 3.6 meter into 0.2. That is nothing but the thickness of the wall, the thickness, into 5.4, which is nothing but the height of the wall, into 20. 20 is nothing but the unit weight of brick masonry, 20 kilonewton per meter cube. So we're just multiplying into 20 over there. So when you multiply that, you get a total load. Hang on. Before that, now we have calculated only the self weight of the wall, just the wall over here. But we will have to calculate even the self weight of these protruding piers. I mean the projections which are happening from the piers. This part is also what we have to calculate. If I break this down into much more smaller pieces, let me just break this. Yeah, if you see the weight of the wall, the self weight of the wall is just that part, just the wall on either side. It's just a solid wall. We need to calculate the self weight of the both projections which are happening on the either side as well. So in that regard, we are multiplying 4. We have 4, 1, 2 and 3, 4 over here. We are multiplying all these 4 into 0.1 into 0.1, which is nothing but 0.1 of 0.1 in one side, the width, and 0.1 in the other direction, the depth. We are just multiplying that and multiplying it with 4 in number, because there are 4 projections like that. And of course we are multiplying the height as well. We have a height element, height coordinate as well, and the unit weight of the masonry unit. So once we do all that, we get the total self weight of this unit, whichever you are seeing over here. We get the total self weight of this separate unit. Now similarly, it is applicable for all the bays out there. This is just for one unit over here. So the total load per bay is 162, which is nothing but the weight of the roof on a bay, plus the self weight, which is 82 kilonewtons. That is these two combined, both the projections and the wall. We get a total of 244 kilonewtons per bay. That is the total load happening per bay. Now there's a small annotated input over here, where area is equal to 3.6 meter into 2.2 meter plus 4 into 0.1 into 0.1, that is 76 into 10 power 4. This is nothing but this top area, the area which you can see on top, the top cross sectional area is what this annotation is about 3600 mm, that is the length between the center to center over here, plus into 200, which is nothing but the thickness, in plus 4 times all the 4 projections. Okay, that will give the total surface area of that particular wall. Moving on, let's go with the effective height. So when it comes to the effective height, the first thing that comes into mind is the support conditions. What is the end conditions on top and bottom of that particular wall to consider in order to get or calculate the effective height? So when we come back to our IS 1905, to calculate effective height, we go back to table 4. Yes, table 4. So in table 4, since both the sides of the wall are restrained, see, it has been mentioned that the top is RC slab. When they mention it anything other than RC slab, maybe if it's a truss roof, maybe you have a different kind of restraint system over there. Since it's an RC slab, it's a fully restrained setting over there, both rotational and lateral. There is no movement, so it's completely restrained. So it will be the first criterion, the first condition of table 4, where the effective height is 0.75 times its clear height. So we just multiply 0.75 times 5.4, that will give us 4.05 meters as the effective height. Let me just quickly check, is everything clear? Are you able to hear me? Are you able to clearly hear me? Can you hear me fluently? Guys, can you hear me fluently? Am I clear? Hello? Guys, can you hear me? Okay, great. Now I'll proceed. I'll continue with the lecture. Right. So coming back to the example, next thing is the effective thickness. Now, again, when we're talking about thickness, there's something called stiffness coefficient that is involved. We always have to consider the factor of stiffness coefficient, which is where thickness of the pier and thickness of the wall will come into picture. Since there are multiple number of piers involved over here, in this case there are 5 number of piers, we will have to consider the stiffness coefficient in that regard. So let me just pull this back to its original position. So the thickness of the pier divided by the thickness of the wall will give us a factor of 2, which is necessary in order to calculate the stiffness coefficient from table 6. So what is the thickness of the pier over here? The thickness of the pier is the distance of the pier, which includes the thickness of the wall as well. So the thickness of the pier with wall included is 400 mm, while the thickness of the wall is 200 mm. So that is depicted over here in terms of 400 by 200. This will give a ratio of 2, while the effective span by effective thickness is given as 3600 by 200, which is 18. 18 is the effective thickness. My mistake. That is the slenderness ratio. Effective span is to effective thickness. That is the slenderness ratio. So 18 is the slenderness ratio over there. So going back to our code in table 6. Under table 6, where is table 6? Table 8. Table 6. So where is table 1? Yeah. Table 6, the stiffness coefficient for walls stiffened by piers, buttresses or cross walls, etc. So we have our TP by TW ratio as 2, 400 by 200, that is 2, which is over here, and that will bring us to column number 4, TP by TW, this one. And the slenderness ratio, SP by SW, that is the effective span by effective width, will be, which is 18 over here, that is somewhere in between 15 and 20. So for a stiffness coefficient of 2 and a slenderness ratio of 18, we will have to interpolate over here. Let me just directly jump into our answer, which is over here. The stiffness coefficient is 1.04, so it is calculated by linearly interpolating. Moving on, the effective thickness ultimately will be the stiffness coefficient into the actual thickness. That will give us 1.04 into 200, which is equal to 208 mm. Okay, so this is the effective thickness that is happening over here. And lastly, the slenderness ratio based on height. When we are talking about slenderness ratio based on height, just a small confusion thing is that I mentioned that SP by SW is the slenderness ratio. It is not the slenderness ratio. It is a ratio which we consider in order to get our stiffening coefficient, in order to get our effective thickness by the virtue of the stiffening coefficient. So don't consider SP by WP, that is the span by width, as slenderness ratio. It can be confusing. I just got confused now. The span of the pier is nothing but the center to center distance between two piers, that is the SP over here, and WP is the width of the pier which is happening, that is the 400 the 200 the width of, oh, let me just show you this one. Yeah, this is the width of the pier, the 200 mm measurement. This is the width of the pier, while this is the thickness of the pier. The thickness is 400 and the width is 200. Yes, there is a doubt. Okay, clear. Next. Moving on, the slenderness ratio is now calculated based on the effective span and effective thickness. Like I always said, SR is always the ratio between effective span and effective thickness, or effective height is to effective thickness. So the effective height over here is 4050 mm, that is nothing but 5.4 into the 0.75 factor which we have done because it is complying with condition 1 in table 4. Now the slenderness ratio over here is 19.5, which is approximated to 20. Oh, we still have 10 minutes. Okay, which is approximated to 20. The SR, the slenderness ratio based on length. Now there are two slenderness ratios. One is effective span is to effective thickness, and two, effective height is to effective thickness. The thing is that we will always consider the least value. This SR of height and SR of length, we should be considering the least value of it. Since SR of height is given as 20, it's 20, this is the slenderness ratio, and then slenderness ratio based on length, that is 2.88 meter divided by 0.2 meter will give us approximately around 4. Now out of these two, we'll be considering the slenderness ratio based on length, that is 14 over here. So with that slenderness ratio, we will be heading towards calculating the stress reduction factor. The stress reduction factor, we can get it from table 9, stress reduction factor based on slenderness ratio and eccentricity. So we won't be taking any eccentricity into factor here. We'll be just considering the eccentricity as 0, since we are going to deal with only axial loads that are happening on top of masonry structures. So for a 0 eccentric load, that is column 1, I mean the first column, this column number 2 over here. For 0 eccentricity, the stress reduction factor can be linearly interpolated. The factor is 0.67. Again, there's a small mistake in the existing material over there. The mistake has been corrected. The stress reduction factor is 0.78. It is somewhere, since the slenderness ratio is 14, we have considered the slenderness ratio 14. And for an eccentricity of 0, we are considering 0.78 as the stress reduction factor. So we'll multiply that 0.78 stress reduction factor to the basic compressive stress which has been found in table 8. Over here, we are going to multiply this to the stress reduction factor which is happening to which was found in table 8, that is 0.96 for 10 Newton per mm square stress. Once we multiply that, that is 0.78 times 0.96, we get a factor of 0.75. Now 0.75 is the allowable stress that can happen the allowable stress by the virtue of existing load is 0.32. So since 0.75 is much more greater than 0.32, the entire design is safe. That means that the total stress that this particular masonry structure can resist. Let me just move this back in place. Yeah, the total load that this masonry wall can resist is the stress it can resist is 0.75 Newton per mm square. But then the stress that has been generated by this virtue of the slab is just 0.32 Newton per mm square. Since this is much more lower than this allowable stress this wall can resist, it is considered as safe. Moving on, this we are just talking in terms of stress. Now when we convert that in terms of load, we are just multiplying that stress with the area which is happening on top of it. The area 76 into 10 power 4. If you recall, we have calculated, it is nothing but the area of this cross-sectional dimension, just this cross-sectional dimension, that is the 76 into 10 power 4 mm square. That is the area. We are multiplying the stress reduction factor, allowable stress, with the area to get the total load that can be obtained. So the total load is 593. When we multiply 0.78 to 76 times 10 power 4, we get 593 kilonewton, which is the allowable load that can go on top of this particular masonry structure. But then our slab is only creating a load of 244 kilonewtons. It's very less. It's more than half less than the actual allowable load. So absolutely the design is very safe. So the wall that has been adopted with that particular thicknesses and that particular span of pier to pier distance is acceptable, and yes, the design is also safe. So this will conclude today's example of design of solid walls supported with piers. So I'll be taking questions. You can just leave a message if you have any doubts, or you can just unmute and say if you have a doubt. I'm just open for questions. If you don't have any, you can just unmute and say you don't have any doubt, question, please. Good morning, Abid. Tell me. Oh yes, I'll be doing that today. I had some connectivity issues past 2 days, so today I'll be uploading both the sessions. Just give me some time. By the end of the day, you'll be having the links of the lectures as well. Any doubt regarding today's session or any session as a matter of fact? Oh, okay. It happens. That's why I'll try to upload the session. Correct. Yeah, I'll try to upload the session anyway, so that it will be easy for you guys to refer. Any doubts? Class, any doubts? Amir, Harshita, Arpita, Ali, Munib, any doubts? Kavya, Aishwarya, Anamika, Reddy, any doubts? Syed, Rajendra, no doubt? Likith, no doubt? Charan, you have any doubt? Okay, great. I'll take this as no doubt session. So since no one has doubts, I'll conclude the session today. We just have 3 minutes before the meeting will hang up. It has a 40-minute deadline. So let's just finish off today's session. In the next session, we'll be starting with walls that are subjected to axial loads. Okay, till now we have discussed about uniformly distributed load. Now in the next session we'll be discussing about axial loads, how the axial load is transmitted to the particular masonry wall and how to design a particular masonry wall with respect to axial loads. So with that, we'll conclude today's session. Thank you all. There have been around 31 to 32 participants earlier. Now it has dropped down to 29, but then it's okay. Okay, then thank you all. I'll conclude.